when we're drawing out our E2 products, so what our alkenes are going to look like from these elimination reactions, these bimolecular elimination reactions, there are three things that we have to keep in mind. So depending on what we're starting with, we might have to worry about the stereospecificity of the E2 reaction, and we'll talk about how the way that the starting material looks dictates how the product has to look and how that alkene has to look. And that has to do with that beta H coming off in a very specific way. So we'll deal with that in the next video. For stereoselectivity, we're going to have to concern ourselves with whether we're going to get a cis or trans double bond. So we'll talk about the transition state for leading to each of those, which one is more stable, so which one is going to be the favored product, but we do have to consider that as well when we're drawing our E2 products because they are alkenes. And lastly, we may have to consider regioselectivity as well. So this is going to be if we have choices of different beta H's that we can take, which one's actually going to be taken. And we're going to see that this actually depends on the base. And so for these three, we can draw in their beta H's. So if we label the alpha carbon, we're going to have for each of these, the alpha carbon is going to be the one that's attached to the leaving group. The beta carbons are going to be beside that, so the one on the left for the first molecule, the phenyl group is a benzene ring, and there will be a beta carbon there, but we're not going to have any beta H's at that part, so we're not going to go ahead and label it right now. We're going to have the beta carbon next to the alpha carbon. All of them for the last one, we're actually going to label both of those beta carbons because we actually will have beta H's on that one on the right-hand side. If we want to draw in our beta H's, we would have one beta H in our first molecule, two beta H's in the second one, because there were two bonds that we were not showing. For the last one, we're going to have the same two on the left-hand side, but we're also going to have three on the right-hand side. So we have many beta H's in the molecule on the right. So when we're concerning ourselves about stereospecificity, if we have one beta H to do the elimination, we have to take this beta H off in a very specific way. We're going to have to do that with all of them, but it becomes very important when you only have one. You have to make sure that you're taking off that beta H in the correct way, and we'll talk about that in the next video. About stereospecificity. For stereoselectivity, the alpha beta bond can rotate, so we can rotate around this bond here, and that means that we can actually take off either of those H's, but we're going to get a cis or trans product possible. But this is going to be something we're going to ask ourselves if we do have more than one beta H on that same carbon, so two beta H's on one carbon. And then for the last one, this is going to be a situation when we have multiple sets of beta H's. So we have multiple beta carbons with beta H's. So that's going to be another thing we have to consider. How many beta carbons do we have in our molecule that actually have beta H's on them? So the reason that this all matters is that we're going to be asking ourselves, for example, stereospecificity, if we have this H, can we just take it off the way that this molecule looks and then we can get an alkene that looks like this one? Or do we have to rotate around what is the 1,2 bond in the way that we numbered this here? So do we have to rotate around it so we can take that H off and get a product that looks like this? So these two are different alkenes because they're different stereoisomers. We have the phenyl group opposite to the ethyl group in this one, and on the same side as the ethyl group on this one, and it's going to matter which product we draw. So we're going to have to pay attention to how that one beta H that we have is actually coming off the molecule. For our second molecule, this is going to be important for whether we're going to get this trans alkene, like this product here, or whether we're going to get this cis alkene, so where the phenyl group is on the same side as the ethyl group. So we're kind of dealing with similar issues in both of these, but in this case we have more of a choice in terms of which one are we going to take off, and we're going to be able to get these two different products. So which one will be favored, that's what we'll talk about in the stereoselectivity video. For regioselectivity, this is going to be probably one of the ones that we can see that they're different the most, because this is what region of the molecule the double bond is going to go into. And so in this first one, we see that the double bond, if we took one of these beta H's, the double bond would be between 2 and 3, so it'll be on that side. If we took one of the beta H's on the end of the molecule, we would actually end up with a double bond between carbons 1 and 2. So that would be a different alkene product. So stereospecificity, we'll talk about how does that H have to come off, and what does that starting material look like? What does that dictate for how the product looks like? For stereoselectivity, there's going to be a choice, but which one of these beta H's is going to be more favorable to take off, and which one, cis or trans, is going to be a more favorable product. And then for regioselectivity, what region of the molecule is the double bond going to end up on? And that is going to be dictated by the base that we're actually using.